Assalamu alaikum. We are going to start with our task 2. So task 2 talks about show how the following logic circuit could be built using the NAND gates only. So in the previous task, what we saw was that we had a combination of NAND and we were told that it is an AND function and we proved that using the truth table. But in this question, what we are doing is that we have normal gates and gate, not gate, or gate, and we have to build using NAND gates only. So what I did here was I actually combined all of these sets. So look at this. Firstly, we have AND over here, we have NOT here, and OR here. So if I go a little upwards and we see the figure 10.34, we can see that this part is AND gate. So this was AND gate part as it is, right? So here it was the NOT gate, so that's the NOT gate as it is. And then later on we had an OR gate that was combining both of them. So this is the entire OR gate and this is the entire OR gate as well. So that's how the combination of NAND was used and we were able to produce a logic circuit like this. So that was what they wanted in question number 1. They wanted us to show something like this, and then they said that complete the truth table for both logic circuit to show that they produce identical outputs. So we have to see if they provide the same outputs as well. So for that, firstly let's solve this one. Write the outputs of this logic circuit, and then we are going to write the answer for this logic circuit. So let's see. We have J, we have K, we have X. Actually, let's write X in the end over here so that we can easily compare. So for J, we have A dot B. A dot B 0, 0, 0, 0, then 0, 0, and 1. For K, we have to do C naught. So 0, 1, 0, 1, 0, 1, 0, 1, 0. For X, we have to do J plus K. So J plus K, 0 plus 1 will be 1, 0, 1, 0, 1, 0, 1, 1. So that's the final output for this logic circuit. So now we are going to implement it using this one. Let's just bold it over here. For example, let's keep this one, let's name this part M, let's call this one N, this is O, this is P, this is Q, and this is R. Okay, let's do this. So we have M, we have N, we have O, P, Q, and R. So for M, we have A dot B. A dot A NAND B. A NAND B is M. So A NAND B would be 0 dot 0 NAND 0 will be 1, 0 NAND 0 will be 1, 0 NAND 1 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 will be 1, 1 NAND 1 will be 0, 1 NAND 1 will be 0. For N we have M NAND M. For N we have M NAND M. So uh, one NAND 1 NAND 1 will give us the value 0. 1 NAND 1 will give us the value again 0. Again 0, 0. Using this 0, 0, and then 0 NAND 0 will give us the value 1, and 0 NAND 0 will give us the value 1 as well. So now we can see up for now for O we have N NAND N. So N NAND N will provide us the values 0 NAND 0 will be 1, 0 NAND 0 will be 1, 0 NAND 0 will be 1, 1, 1, 1, 1 NAND 1 will be 0, 1 NAND 1 will be 0. So now we have to do the P part. For this one we can see that we have to do C NAND C. So C NAND C will be 0 NAND 0 will be 1, 1 NAND 1 will be 0. Similarly, it will be done like this. Now for the Q part, we have P NAND P. For P NAND P, we are going to have 0, 1 NAND 1 is 0, 0 NAND 0 is 1, 1 NAND 1 is 0, and then again something like this. So that's what will happen here. Now we have O NAND Q. O NAND Q. 1 NAND 0 is going to be 1. 1 NAND 1 will be 0. 1 NAND 0 will be 1. 1 NAND 1 will be 0. 1 NAND 0 will be 1. 1 NAND 1 will be 0. 1 0 NAND 0 will be 1. 0 NAND 1 will be 1. So now this is the output for the next part, for this logic circuit. So if we see, we have identical values each time, so that means that they actually show the identical outputs. So that's it for question number 1 from task 2. Now we're going to move on to question number 2. So the question number 2 talks about show how the XOR gate could be built from NAND gates only. We have seen how to make how to make AND gate using NAND gates, NOT gate using NAND gates, OR gate using NAND gates, but now we have to see how to make an XOR gate. So they are saying that complete the truth table for your final design to show it that it produces the same output as a single XOR gate. So we will prove that using the truth table, but firstly let's form the NAND gate. So what we will do firstly is that we have to know this priorly, that when we are doing A XOR B, it is basically something like A dot B dash plus A dash dot B. It's just a very simple expression that is repetitively being used in A levels of computer science as well, and it is something that is known to almost everyone, which is this formula, right? That A XOR B is equals to A and B naught plus A naught and B, or not A and B, something like this. So this is the main thought behind this. So let me make an XOR table first. So for this one, 0 and 0, A XOR B will be 0, and 0 1 is going to be 1, 1 0 will be 1, and then when we have same inputs 1 1, we are going to get a value 0, right? So this was the formula, this was the truth table of XOR gate. We can see that we need some NOT gates here, we need some OR gate, and we need some AND gates as well to represent it. So when we have to only make using the NAND gates, we can see that mm if I actually just let's just go a little backward and then we can talk about it a little more. So over here we can see when we are talking about a NOT gate, we are also talking about A NAND A. That was the main idea behind this, right? And when we are talking about OR gate, we were saying that it's basically this portion is A NAND A, this portion is B NAND B. But if we look at this portion is also this portion this portion is also the same as this one, which is actually a NOT gate. So instead of B NAND B, can I write B not and not A. Not A and not B will be suitable because this A and A is same as A naught. We have proved that in task 1 as well. So A naught, B naught. So this is the final NAND product. So not A, NAND, not B. This will be the final result for the OR gate. If we talk about the AND gate, we can see that what it is doing is it is giving us firstly A and B, and then it's the NAND of this. So the final answer would look like this: A and B, NAND A and B. Let me write it down. It will look like this: A and B, NAND A and B. So for XOR, it's the combination of all of it. What we have to do is let's just make a truth table step by step, and then we can see how it will turn out. Right. So we have A B. We will have A NAND A not A, not B, and then we will have A dot not B and A dot B, and then we will have the final XOR output. So this will be the very simple. This will give us the same result as earlier as well. So this is not very important. This two table is not very important, but it is. I'm doing that to confirm that this expression is the same as this expression will give us the same result. So we'll have 0 over here. A dot B dash will give us 0 0 1 0 0 1 0 0. I know by this time you can easily go and check, cross multiply all of it. So we'll have 0 1 1 and 0. So that's how it will work. Also, how we derive this one, we have already been discussing this, that if we have these are the two outputs 1 1, so A naught and A and B naught, and then we have to add by using the operator OR. So this is how this expression was made, right? So there is no problem with this one so far, I think. Now, how we came to the conclusion of the diagram, let's talk about that first. So I made this diagram for to understand it. So what I did was I just used this expression and I drew a diagram out of it. So we had A, we had B, A and B naught. So we will get A dot B naught. We have A naught and B here. So A naught dot B, or not A dot B. So that's how it became, and then we added that. So we got the final output A XOR B. So this was the gate. So now what we can do is we can use these chunks and input them over here, and it will be very quickly be done. It will be it will be done very quickly. So let me move this one over here, and I'm just going to integrate these as it is, and then we're going to further talk about it. Alright, so I just drew this circuit, and we can see wherever I use this AND gate, I implemented that over here. This might look very confusing, but let me explain it to you, and we're going to look at one by one. So we have this AND gate. No, firstly let's look at this NOT gate. Okay, so this is the B, and this is the B NOT gate over here. So this is the B's NOT gate over here. NOT gate is just made by the input that is repeated. So we will have a NOT gate over here. This is the NOT gate, this is the NOT gate. So now, and if we talk about this NOT gate over here, that is coming from A, we just made one NOT gate as well. So let me highlight, this is the first NOT gate, this was the second NOT gate. Alright, now what we did next was this was an AND gate. For an AND gate, we have to use two inputs, and then we have to do a repeated input. So firstly we had a one input and then a repeated input, something like this. So here it is our let me actually change the color of highlighter so that we can easily see AND gates. So this and this combined is our AND gate. Okay, actually, I think we should switch it to a lighter color so that is it's visible. All right. So this is our first AND gate, and if we look at this one, we will have a similar one downwards as well. That's our second AND gate. This AND gate. Okay. This was the AND gate first. This was the second AND gate that we drew, and now this last part we can see this is an OR gate, and an OR gate's representation is something like this. So you can see this is officially the XOR gates um, logic circuit using all NAND gates. But if we look at it, there are some repetitions over here which are not useful and which can be neglected. So we'll see that. Although this answer, if you write this logic circuit as the answer, it is all right. It will be marked correctly. But there are so many redundant and unnecessary NAND gates present over here. To avoid that, what we are going to do is just give me a second. Oh, let me charge my laptop. Well, instead of drawing it, we can already see it first. Let's remove this one. And if we see this part, let me circle it. What does this part means? This was some answer. Let's call it. Its the answer is one here. Okay, we are getting one here. So we had an immediate NAND gate which has a repeated inputs. We have repeated inputs in NOT gate. Whenever there is a repeated input, that means it's a NOT gate. So one will convert and it will become zero over here. And then we have another inverted similar NAND gate. So zero will become one. So in the end we still have one. So these two does not mean anything because the values we are getting are the same. And let's say we have 0 over here, it turned and the complement was 1 and then again it was 0. So we are getting 0 and 0. So these four are not necessary. So what we will be left with, we'll have A, we'll have B, and then the let me draw it nicely. Now we can see that we have simplified this XOR gate and now we have a similar one but in a shorter form. Now we can see that we have removed the redundant ones and we have finally got our XOR gate that is very much simplified. We can do some more extensions and we can remove this and this one and we can just have one NAND gate that will do their job, but we can keep it as it is as well. So I'll sum it up over here. Firstly, what we did was we drew our NAND gate formula using the truth table, and then we looked into how it will be made, what will be the operators that are going to be used, that are NAND and or and NOT gates, and we looked at the logic circuit and then we cut down the logic circuit and reduced it and made it very simplified in a very simple manner. So that is it for task 2.